First glance, yeah, okay, this equation maybe isn't very interesting. You learned a lot of what there is to know about it all the way back in high school algebra. But we're going to add an extra requirement to it. We're going to add the requirement that x and y have to be integers. And that turns into what was called a Diophantine equation. The name goes back to Diophantus of Alexandria all the way back in the 3rd century. And this makes them a little more interesting. Uh, Not so much for us just yet. We're actually going to have to push this a little bit further. The question we want to answer here is, if we make this restriction, if we turn this into a Diophantine equation, how many solutions does it have? And if we just say x and y have to be integers, then the answer is there's still going to be infinitely many. Pick any value you like for y, let x be 5 minus that, and you get a solution. Y can be any integer, x can be any integer. There's infinitely many solutions. It's not very interesting yet. All right, so we're going to add one additional requirement. We're going to take this a little further and say that x and y have to be greater than or equal to 0. Okay, now things start to get a little more interesting. Now, yeah, there's going to be a finite number of solutions to these things. Now, I picked a pretty straightforward one for us to start with, where there's just two variables. Here, you can figure it out pretty easily without recourse to any of our counting methods. The smallest value x can have is 0, because that's our restriction. And the biggest value x can have is 5. If x goes beyond 5, if it goes up to 6, then y is going to have to be negative, and that's not allowed. Right? So x can be any number from 0 up to 5. Once we pick the value of x, the value of y is determined. It's 5 minus that. Right? So whatever method we come up with here, whatever general method we come up with, for this example, it better give us 6 as the total possible number of solutions. Okay, so here's how we're going to approach this in a way that will let us answer even questions with more variables and bigger numbers. All right, think of that 5 as being split up into 5 ones. So there's 1, 2, 3, 4, and 5. And I have to put, because there's two variables, I have to put one divider in here somewhere to split these up. So for example, if I put my divider here, I would get 2 plus 3. Right? If I put my divider here, I would get 4 plus 1. And I can put it all the way at the end. For example, if I put it here, then I would get 0 plus 5. Right, so hopefully you're starting to see how this connects back to what we talked about in an earlier lecture here, where we're talking about selecting objects with repetition. Right, I really have one choice to make here. Where am I going to put that bar in this set of 6 spaces? Right, because there really are 6 spaces here if you count one for each of the ones plus the one that I'm going to put the bar in. Right, so how do we work this out? Well, I have 6. I have to choose one space from a set of 6 to get that bar. Or if you want to tie this back to the formula we saw, remember our formula was n plus r minus 1. Choose r. R is going to be the one space, right? N is the number of objects. That's 5, right? Because I have 5 ones that I'm dividing up here. Either way, right? If you go to the formula, this is 6 factorial over 1 factorial times 6 minus 1. That's 5 factorial, and yeah, look at that. It came out to 6, right? Exactly the result that we expected it to come out to. So I've got a slightly more complicated problem here. Now, first, instead of 2 variables, we have 4. So it would be much trickier here. Try to just kind of write things out and reason our way through how many possible solutions there would be to this. But that's okay. We can still work this out. But just to make things even more interesting, I've added this additional requirement here This time we're not just going to require that w, x, y, and z have to be integers. We're also going to require that they have to be greater than or equal to 1. All right, so how does this change our process? Well, again, I'm thinking I'm going to break these things up into 4 groups, one for each variable. And now, instead of starting off with 21s like I did before, every group has to get at least 1, 1. If I do that, this condition is going to be satisfied. In fact, I have to do that. Right, so now what do I have left to work with? Well, if I take away those 4 1s, I have 16 1s left that I have to put out here. So I'm going to put 1, 2, 3, 4, and so on out to 16 of these. And then I need 3 more spots that I'm going to put the lines that I do the separating with. Right, so I have a total of 19 blanks, if you will, that I have to fill. 16 of them are going to get 1s, and 3 of them are going to get those dividing lines. Okay, so now I can answer the question, right? I have 19 spaces to choose from, and I have to choose 3 of them to get those dividing lines, right? Number of ways I can do that is 19 choose 3. And if you go to your calculator, work this one out, this comes out to 969 possible solutions to this equation. So this wraps up our discussion of permutations and combinations, right? In the next section in this chapter, we're going to do something a little different. We're going to kind of go back to your algebra class a little bit, and we're going to look at what are called binomial expansions. Right, we're going to look at expressions like 3x plus y to the 12th. Now, if you wanted to multiply this out, that would be a fairly long and tedious process trying to do this by hand, right? But in the next chapter, we're going to look at this thing that's called the binomial theorem, and it's going to give us a really quick way to expand this thing out using the combinations that we talked about in this chapter.